Hello, in this video I describe one of my own algorithms implemented in Rust, which is used to identify RS chiral centers of compounds of different complexity, and although some of the parts of this video can be considered educational, it's more like a devlog where I discuss the development process at its current stage, which is far from over. Although I have tested this algorithm on a limited set of compounds for the debugging purposes, this set was really quite tiny, only 22 compounds, and usually we deal with thousands, hundreds of thousands and billions of compounds. Despite it is still work in progress, I want to share what I have already done in this direction. Well, the crate that I developed is not a Cheminformatics crate. It requires a lot of basic Cheminformatics stuff, and the crate itself is more like a general purpose modeling crate with emphasis on molecular mechanics. The most common molecular structure representation used by Cheminformatics tools is molecular graph representation, in which atoms are nodes and edges are bonds between them. And there are two approaches which you can use to analyze molecular structure in complex cases, namely depth-first search, which is a recursion based and which allows you to go deep through each connection attached to your root node. For instance, you can use it in cycles and ring detection algorithms, or if you want to find a path between two nodes, shortest path, for instance, between two nodes, you can also use depth-first search. And unfortunately, it is not applicable for this particular problem that I'm going to cover in this video. And this problem is solvable by using breadth-first search, in which you move from your root node shell by shell until you cover enough of the atom environment to make a certain decision. As it is demonstrated in this particular image, we start with root node, we then go cover the first level connections of this node, and this we can do using basic for loop iteration. However, if you want to go deeper, then we will apply breadth-first search, and this would require for us to use data structure like QUIF, which is a first in first out data structure, and this is particularly what I'm going to use for my RS chiral center identification algorithm. So at the preliminary stage of the search for RS chiral centers in our molecule, we first must select atoms that can potentially be chiral centers. Such atoms must have 4 connected substituents. After we have selected our candidates, we then iterate over each of them. We create a chiral center, which we further populate with atoms of each substituent. Now, to do this, we use breadth-first search. So we create a QUIF, and we put in a QUIF our anchor atom, our potential chiral center atom. Then, while this QUIF is not empty, we perform breadth-first search. So first we pop the front atom from a QUIF. At the first iteration, this is our anchor atom. We then process each atom using a logic that I have separated into a function process atom stereo environment. Now this function for each atom, input atom, it gets the connections of this atom, and it collects all the required information to decide what to do next. So here we apply a simple optimization. We store all atom expansions or its closest neighbors already processed in a hash map, and we check if there is a key with our atom's ID. And if there is, we just clone such branches and we skip the step with actually processing atom neighbors. Then we also want to skip all the atoms that are already in our chiral center or are contained in some of the substituents. Further, we select whether this is our first level of breadth-first search. Then we need to create actual CIP groups and to add the first root node of each group, which is the atom directly connected to our anchor atom potential sterile center. And if it is not the first level of breadth-first search, we then simply to each existing group we add branches collected using this approach, and we then continue. So we get back to our scope of our function where we actually perform breadth-first search, and we check if there are any atoms left to process. If there are no atoms left, we then decide what to do next. So first we need to check whether we can distinguish the priority of each substituent. In this case we have 4 substituents in RS chiral center case, and then if there are no groups with equal priority, we then can finally proceed to the last stage of our search. Particularly we sort CIP groups by their priority, and then we assign RS order using geometrical criteria. Now if there are still some equal priority groups left, we then proceed with breadth-first search. And there are 2 outcomes. Either we at some point can distinguish the priority of all 4 substituents of our chiral center, and in this case we do what I have already told you. And if we cannot distinguish all 4 substituents, then we cannot finish our chiral center. Basically this is the case when we run out of atoms to expand it further, and so in this case we conclude that this particular atom candidate is not a chiral center. Now before we get to the geometrical criteria, let's review our structures to hold data. So we have at the basis of all of this stereo unit, which takes one generics, and this generics depends on the particular stereochemical analysis that we perform. So in case of RS stereochemistry we have RS stereo order. Yes. In case of EZ stereochemistry we have EZ stereo order respectively. And so each such stereo unit has our anchor ID, that is the atom from which everything starts, and in RS stereo center case it is also the chiral center. And we also have CIP groups, our substituents, and we have stereo order. We have 2 similar structures to store all this data. One is our finished stereo unit, and this stereo unit is exposed to our client, right? So it's the code that is accessible to a person who writes some application using this library crate. And there is also unfinished stereo unit, and which can be converted into the finished stereo unit if we collected all the required information and all the rules of CIP are satisfied. All the CIP rules are satisfied. So we then have implementation of different methods of our stereo unit unfinished. And there is one important method, which is get groups with equal priority. I have already mentioned why we need it. So we, as you can see here, we directly compare CIP groups, the last shell of our CIP groups, and to do that we implement partial equality and partial order for CIP group. Here we define the logic to actually compare our last shells, and it follows strictly CIP rules. Basically, we are looking for the last expansion layer of our CIP group, of our substituent, and if when we compare two substituents, if we can distinguish between them, then we can also sort them in priority order, and we can assign priority to each one of them. So we are performing breadth-first search until we find 4 distinct substituents, and we can prioritize them based on the last breadth-first search level of expansion. Initially we only check if there are equal groups and expand our search further, but later we perform sorting. If we have found 4 distinct groups, we sort them, and then we can proceed to our last step to determine whether this is R or S chiral center. And this is basically algorithmic and reflection of what we will do manually to determine it. So first we move our system. In this case, this is chiral center, right? And with all of its substituents and atoms, we move it to the origin, but we only analyze basically the root atoms of each substituent, which are attached directly to our possible chiral center. We need to determine their relative order, right? So first we move it to the origin by subtracting our anchor atom coords from each root substituent atom coords. Then we do what we will do in real life. Basically we take our lowest priority group and we align it, perform rotational alignment of it with the axis, which in real life we will just put it outwards from our point of view. Programmatically this is alignment with the axis, and then this simplifies our three-dimensional problem of determining order of our groups based on their priority according to CIP rules. We basically project our three-dimensional coordinates of our root atom in each substituent onto the xy plane, and then we calculate the cross product of positions of our two-dimensional atoms, and we calculate the signed error. Further, we based on the signed error, we determine whether it is sinister or it is rectum, or counterclockwise or clockwise. And if we cannot determine it because our signed error it did not pass certain threshold defined here, in that case our analysis is inconclusive. We cannot decide that this particular candidate atom is a chiral center, so we cannot finish our chiral center. So I have already determined that our algorithm works fine on this limited set of compounds, limited set of 22 compounds that I have picked based on their distinct stereochemistry. Now let's illustrate how algorithm actually simplifies what we will do manually by looking at the simplest case, one of the simplest cases, the ibuprofen molecule. And as you can see, I have already labeled all the atom indexes in it, And our algorithm, it has found that our 7th atom is in fact the anchor atom of a chiral center. And we can clearly see that there are 4 different substituents attached to it. So initially we start with looking only at the closest neighbors of our 7th atom, which is the 19th hydrogen neighbor, and it is the lowest priority group. We can rule out it at this stage, but in the case of all other group at this level of expansion, we can see that we have carbons in each case, so we need to expand further. And at the second level of expansion, we can finally identify all our 4 distinct substituents and prioritize them based on the CIP rules. And now we can assign the order of our chiral center. So we start with highest priority group, which is here, then we go to the second priority group and to the third. And we can clearly see that it is in fact the clockwise order, so our algorithm have successfully identified, as you can see it here. And I have also checked all other molecules, some of them manually, some of them I have determined that it was correct based on the isomeric smile string available at PubChem. But in all cases it was correct. It just there are really complicated cases. I will show you now. Like this, for instance. Molecules with complicated stereochemistry. And some of them have multiple RS chiral centers. So although this set is very small, it is also very distinct. And I think that it clearly demonstrates that in most cases my approach will work fine, but we also of course need to thoroughly test it further with larger data sets. Let's pick one complex case with multiple chiral centers. Let me see. So we have, for instance, our last compound, oxycodone, with PubChem ID 5284603. Let's see if it has isomeric smiles in PubChem. All those molecules are from PubChem, by the way. So we can yeah, here it is, and it has isomeric smiles. We can even see it from here. So in smile strings, in isomeric smile string, each such character indicates the chiral center, and we can count basically chiral centers here based on those characters. We can see that our algorithm have identified 4 chiral centers, and we can count all those centers in one-dimensional smile string, which is 1, 2, this counts as 1, 3 and 4. So we are looking in this case for chiral centers attached to carbon atoms. This one, this one, this one, and this one. And it is the last compound. We can actually visualize those by labeling our atoms. So one is unsure that atom 6. Here, as you can see, it's part of complex system of cycles, rings. And another chiral center is at atom 7, again for substituents distinct. And this is actually the case when my optimization strategy should give better performance as compared to totally naive approach, where each time you start expansion from scratch, ignoring all overlapping subproblems. But I'm pretty sure I can optimize it further for such complex cases. So that's it.